again. You guys will get sick of me pretty soon. So Kat Buxton and I are your presenters today in this first workshop of the series. We were on the planning team for the series, and we felt that we could frame it well since we knew who else would be presenting and what they would be bringing to the sessions. I'm going to be presenting on some of the science of climate change, but I also want to be very clear that climate change is not just a scientific issue. It is a justice issue. It is a social, economic, and cultural issue that cannot truly be addressed through just more technology. We must, as a society, look critically at the systems we use that have gotten us here. With that in mind, we chose speakers for the series who could speak towards lots of different aspects of climate and community resilience. Because of my particular background and the trust that I have that you will all come back to the next events to hear from those speakers, I am focusing today on the sciencey side of things. I've been working to better understand the Earth and its systems so that I can attempt to fathom some of the impacts that my choices and the choices of my community are having on the whole world. The content that I'm presenting is some of what I've learned and felt might be useful to share with you all. I look forward to the new questions that come out of today and to continuing these discussions. All right, let's get started with the foundations of energy and matter and how they relate to climate change. So, climate is the long-term average of weather. Weather is the way the atmosphere is behaving. I apologize for how that is set up on the screen. Weather includes the components such as temperature, pressure, wind, humidity, precipitation, and cloudiness. Therefore, climate change is changes from the long-term average of those components over an area, be it a town, a watershed, a bioregion, a continent, the entire world, or some other area. When we talk about climate change, sometimes we talk about global warming, and that is one piece of this. Global warming means that the average overall temperature of the world on an annual basis is increasing due to an amplification of the greenhouse effect. We'll get into more of that soon. Other aspects of climate change involve disrupted energy distribution patterns. Air and water move energy around throughout the atmosphere, and when those movements change, climate changes. When we talk about these ideas, we are talking about changes that fundamentally alter life as we know it on the planet. These changes impact habitat ranges and resource availability. We are experiencing mass migrations, mass extinctions, wars, economic collapses, and many other consequences of those changes. So let's try to understand some of why this is happening. You'll be seeing this slide a lot today. It'll serve as a table of contents to guide us through the presentation. What it's showing is a clearer summary of the previous slide, indicating that climate change is the amplification of the greenhouse effect and changes in energy distribution. In order to understand those ideas, we need to understand the fundamentals of matter and energy. We will dive into energy distribution by discussing the modes of energy transfer, which are radiation, convection and conduction, and latent heat. So let's start with matter. Matter is the stuff that makes up Earth's systems. It's every subatomic particle that makes up every atom, that makes up every molecule, that makes up everything. Air, soil, oceans, buildings, humans, plants, dogs, cats, everything. Humans decided to name atoms based on how many protons are in the nucleus. So an atom with 1 proton is called hydrogen, with 6 protons is called carbon, and an atom with 8 protons is called oxygen, and so forth and so on. Around the nucleus are electrons that we will talk a little bit more about later when we get into radiation. So where did all of this matter come from? There are many understandings of how the Earth and its matter came to be. This includes various creation stories from indigenous cultures and religions around the world. For today, current Western scientific theory tells us that matter came from the Big Bang 13.7 billion years ago. In terms of Earth, it left a cloud of cold dust particles that about 4.6 billion years ago was disturbed and collapsed under the force of gravity to form our solar system, including our sun, the Earth, and the other planets that orbit our sun. Just a quick side note here, there are at least 200 billion suns in our galaxy, the Milky Way, and there are millions of other galaxies in the universe, just for some perspective. Today, the Earth functions almost completely as an isolated system in terms of matter. This means that there isn't any new matter coming from outer space, barring the occasional asteroid, and we aren't losing matter to outer space. This means that matter cycles through Earth's systems. It doesn't come and go from outer space, it just changes form and moves between Earth's own systems. This is a critical idea for understanding that the carbon and water cycles that influence our climate. Again, more on this later. Now, moving over to the fundamentals of energy. Energy is what is required for matter to change. Now, unlike for matter, the Earth is not isolated in terms of energy. There's a constant flow of energy in from the sun and a constant flow of energy out of Earth's systems to outer space. Therefore, we are often concerned less with energy cycles and more with energy balances on a global scale, meaning that we want to know that the amount of energy coming in is the same as the energy going out. Otherwise, we are gaining or losing energy, and that means heating up or cooling down on a global scale. This can lead to global warming. The modes of energy transfer are radiation, conduction, convection, and latent heat. Those modes are represented on this diagram here, which I'm sure you've all seen in one form or another before. This is the Earth's energy budget diagram from NASA that I think is really helpful for understanding these concepts because it breaks them down into pieces. What I think is really critical to understand here is that in any discussion about energy on Earth, there are three systems or layers that we are thinking about. We're thinking about outer space, what's coming in from it, which is largely just from the sun, and what's going out into it. We're also thinking about the atmosphere, this region around the surface of the Earth that extends away. By one estimate from NASA in 2017, the atmosphere extends up to 6,200 miles away from sea level. Most of the mass of the atmosphere, 75 to 80%, is in the troposphere, which is the layer that we live in, the first 4 to 12 miles, depending on latitude and season. This is also where our weather occurs. And then lastly, we're thinking about the surface of the Earth, meaning the land and oceans, surfaces, meaning buildings and trees, farms, mountains, glaciers. Everything that isn't floating in the atmosphere is the surface of the Earth. Here's just one more way to visualize this idea, making sure that we keep in mind that there are three different layers that are interacting with each other. Now, getting to how energy moves between these three layers, let's start with radiation. As you can see here, radiation is the major mode of energy transfer when we're talking about Earth's energy balance. All of those boxes represent a specific component of radiative exchange. The other two on the far side of the diagram will be discussed later. So, what is radiation? Well, I'm so glad you asked. It is radiant energy. It is transferred by photons, which are discrete bundles of electromagnetic energy that travel at the speed of light and behave both as particles and waves. All things with the temperature above absolute zero radiate energy constantly. Radiation is still a subject of intense study, and it can be really hard to wrap our heads around. So for us today, we're curious about the ways that radiation interacts with matter. On a molecular level, radiation can be absorbed, emitted, or scattered in different directions. The arrangement of the electrons and nuclei within the molecules determines what will happen to a photon of radiation of a given wavelength. This is the crux of the greenhouse effect. We'll talk about that a little bit more later. When radiation interacts with a material on a larger scale, we talk about what percent is absorbed, reflected, and transmitted. Together, these three components add up to 100%. Absorption increases the internal energy of the matter by exciting electrons and impacting chemical bonds. This can increase temperatures because temperature, after all, is just the average kinetic motion energy of the molecules. Reflection is when the matter scatters the radiation back in the direction it came from. On a global scale, for solar radiation, we call this albedo. Transmission is the scattering of the radiation along its original trajectory forward. Transmission leads to something called windows, where the majority of radiation of a certain wavelength passes through. In Earth's clear atmosphere, we have these windows around wavelengths of radiation in the visible light range from the sun, where the rainbow is shown on the diagram, between 8 and 14 microns from the Earth, which is a little bit further over. And then we also have it in the range of radio waves. So let's talk about radiation in the three layers that we were talking about earlier: outer space, the atmosphere, and the surface of the Earth. In outer space, the sun is sending radiation away from it in all directions. Our Earth happens to be in the pathway of some of that radiation, which is great for us. The Earth's atmosphere interacts with the radiation from the sun in all the ways that I mentioned before. Some of this radiation gets absorbed by the atmosphere and the Earth's surface, causing them to warm up. They warm up, but they don't get as hot as the sun. Because of this temperature difference, the average temperature of the sun is about 10,000 degrees Fahrenheit, and the average temperature of the Earth is about 58 degrees Fahrenheit. The wavelength and the total amount of radiation coming from these two entities is very different. That's what's being shown on the chart in the upper corner. The sun gives off more radiation than the Earth. Think about the area under the curve as the total amount. Going back to calculus for you guys. And the sun gives off most of its radiation in the wavelength range from 0.1 to about 3 microns, whereas the Earth gives off most of its radiation in the range from 8 to 20 microns and longer. For this reason, we generally refer to the radiation from the sun, or solar radiation, as shortwave, and the radiation from the Earth, also called terrestrial radiation, as longwave. Focusing for a moment on shortwave radiation from the sun, let's detour into photosynthesis. The wavelength of radiation from the sun that gets through the atmosphere and reaches the Earth's surface is largely in the visible light range. We call it visible because the human eye has evolved to be able to differentiate the wavelengths in this range and has associated them with different colors in our brain that we call red, blue, green, etc. Luckily, plants have also evolved to be able to use this range of wavelengths to their advantage. The chlorophyll molecules in chloroplasts absorb visible light strongly in the blue and red wavelength bands, and less so in the green band. That's what's reflected for our eyes to see. The absorbed radiation causes electrons in the chlorophyll to get excited, and that triggers a chain of reactions that produces sugars or carbohydrates that get used by plants to build their cells, and they also get sent out through roots to feed the soil life underground. Kat will talk a little bit more about that later. It is really interesting to think about how fundamental radiation is for life on Earth. Along that same line of thinking, the fact that different molecules interact with certain wavelengths differently is also key to making our planet habitable by maintaining a temperature suitable for life. With this, I am referring to the greenhouse effect. Without the greenhouse effect, the average temperature of the Earth would be near 0 degrees Fahrenheit. The greenhouse effect is a result of the fact that the gases in the atmosphere transmit shortwave radiation through to heat the Earth, but some of them scatter long-wave radiation coming from the Earth in all directions, including back down towards Earth. That's the reflection back to us. This effectively traps some of the long-wave radiation and keeps the energy from being released to outer space. Most of the gases in the atmosphere don't interact with long-wave radiation in this way. Only greenhouse gases do. Depending on the location and time of day, the atmosphere is made up of 0 to 4% water vapor, which is the most abundant greenhouse gas by far. And then about 0.1% of the atmosphere is made up of a combination of other greenhouse gases, like carbon dioxide, methane, nitrous oxides, fluorinated carbons, and ozone. These gas molecules are well suited to perform this task, to keep the planet habitable. However, getting back to climate change, the carbon dioxide argument often made is that humans have disrupted the carbon cycle to the point that more carbon dioxide molecules are in the atmosphere than ever before. This, therefore, amplifies the greenhouse effect and changes the Earth's energy balance, causing the Earth to warm. A few nuances here that I find really critical. Humans have increased the amount of carbon dioxide in the atmosphere, but thinking back to matter in Earth's systems from earlier, the actual total amount of carbon on Earth hasn't changed. We've just changed the way that the carbon cycles. Carbon that used to be in the ground as fossil fuels, in vegetation for most of the year as biomass, and in soils as organic matter, is now in the atmosphere because of our power plants, engines, and agricultural and land management practices. Another detail is that the carbon dioxide levels in the atmosphere are not just constantly increasing every day. I know that we all hear that the levels are up to 415 parts per million, when a safe level might be 350. But just keep in mind that those numbers are the annual averages of the CO2 levels in the atmosphere. Over the course of the year, carbon dioxide levels in the atmosphere go down during the time period when it is summer in the northern hemisphere. This is because the majority of the terrestrial landmass on Earth is in that northern hemisphere, and summer is the growing season for most of our species of vegetation, including what we farm for food. This means that photosynthesis on planet Earth is working its hardest to take some of the carbon dioxide from the atmosphere and transform it into biomass. And one more detail, just to add to it. The oceans, in addition to the atmosphere, have been carrying a large portion of the carbon that is no longer found in terrestrial ecosystems. Earth's oceans have absorbed about 31% of our carbon emissions since the Industrial Revolution. This means that if the world does figure out a way to reduce the concentration of carbon in the atmosphere, the carbon stored in the ocean will begin to be released back into the atmosphere, lengthening the timeline to reestablish a carbon cycle. So that's the carbon cycle. Here's the water cycle, which is another major thing that we've messed with. Don't forget that water vapor is the most abundant greenhouse gas, and so changes to the water cycle also strongly impact the greenhouse effect. Just a few of the ways that we've altered the water cycle include removing vegetation, which disrupts the soil-plant atmosphere continuum that moves water through transpiration, the extraction of water resources from underground aquifers to bring that water into our fields, channelizing our rivers and stormwater paths to move water off the land and out of cities into the oceans as quickly as possible, paving and covering soil, which reduces infiltration, and we've also added particles to the atmosphere that change the way that clouds form and precipitate. We'll come back to the water cycle soon to dig in a bit more, but I'm bringing it up here because people often forget about the water vapor component of the greenhouse effect, which deals directly with radiation. Okay, so deep breath. That was our overview into radiation. It's a big, complex mode of energy transfer that drives a lot of the energy balance on Earth. But it's not the only mode of energy transfer. Let's dive into these other ones. Conduction and convection involve the movement of sensible heat, or heat that, when moved to a new substance, causes the temperature of that substance to increase. You can sense or feel it. Conduction is the transfer of heat by direct contact. On a molecular scale, when heat energy moves from molecule to molecule as a result of collisions from vibrations. Like in the image when your hand touches a hot pan. My apologies. Convection is the transfer of heat by the mass movement of a fluid. A fluid is just a liquid or a gas. And here we're talking about billions of molecules scale. The circulation of water in a pot of boiling water demonstrates convection. In the Earth's energy balance, conduction and convection move energy between the Earth's surface and the atmosphere. For this piece, solar radiation comes through the atmosphere and heats the surface of the Earth. Then the molecules in the air immediately above the surface of the Earth get heated by conduction. The air molecules are touching the warm ground molecules. Those air molecules then move as an air parcel away from the surface of the Earth because they are warm and they want to cool off by spreading out and getting away from the heat source. This motion forces other air molecules down toward the surface of the Earth, and this cyclical motion is known as convection. Because the sun's radiation is not evenly distributed across the surface of the Earth due to the Earth's rotation, albedo, and the angle of incidence of the sun, the radiation, conduction, and convection patterns are different at different locations, which drive pressure gradients, wind, and storms, things we call weather patterns. Now, maybe you'll have noticed that in this upper diagram shows latent heat release too. We'll address that now. So again, latent heat is just another mode of energy transfer. Excuse me. It involves the water cycle in clouds, and it is the last piece of our energy budget. Latent heat is hidden heat energy that changes a substance from one phase to another without changing the temperature of the substance. Some examples of phase change where latent heat is involved include changing from a solid to a liquid, known as melting, or from a liquid to a gas, known as vaporization. At pressures and temperatures commonly found on Earth, groups of water molecules can regularly be found in all three phases: ice, liquid water, and water vapor. At the surface of the Earth, water can evaporate and transpire through vaporization, meaning that a liquid water molecule can absorb enough energy from the substances around it to be able to be released from the molecular bonds with other water molecules and enter into the atmosphere with other gas molecules, like nitrogen and oxygen. This can cause localized cooling. The water vapor molecule holds onto that energy until it condenses, at which point it is given off to the matter it condenses on as translational energy in chemical bonds. This new movement increases the temperature of the matter that the water vapor condensed on. When that happens in a cloud, it increases the temperature of the cloud and thus increases the amount of radiation given off by that cloud. Latent heat transfer emphasizes even more just how important the water cycle is to energy dynamics on Earth. In addition to being a greenhouse gas and moving around latent heat, water in the form of clouds impacts albedo and radiation transfers. Oceans absorb CO2, glaciers melt with increasing temperatures, contributing to positive heating feedbacks. Sea levels rise because more water is in the ocean and the oceans are warmer and expanding. And it's all very complicated and interconnected. It requires anyone who is thinking about changing climates to think about whole systems and complex interactions. And thinking in this way is necessary because it's the only way that we can truly understand what's going on. From a science perspective, we've now gone through each of these components of the Earth's energy budget, and hopefully there's a greater collective understanding of what we mean scientifically when we say climate change, of what's really going on with the long-term averages of temperature, pressure, wind, humidity, precipitation, and cloudiness, and how it is fundamentally altering life as we know it. So now what? Some people want to use this information to engineer new technologies to control these systems. Others want to figure out how to replicate pieces of these systems so that we can live on other planets. Even still, others have decided the Earth will balance herself out without our intervention. And others anticipate the end of the human species. I think that by understanding these ideas, we can try to undo some of the damage that we've caused and make better decisions. Luckily, Kat Buxton, who will be speaking next, is here to share some of her ideas about how to do that by managing our land and systems differently.